Hello everyone, welcome to my YouTube channel once again. We're going to continue with the reservoir simulation training series, and this is the second lesson. The first lesson ended at this point where we're trying to view the results. So after the simulation run, some results have been generated. Let me take a second to show you samples of those results that we're talking about. I'll go back to the data manager, click on the summary section, and here is what we'll have. The first notable thing you're going to find on this summary section data manager are these two buttons, keywords and then selected. Selected shows you the result vectors that have been selected that you're interested in viewing. Then on the keywords tab, you have a couple of groups of results here. Okay, so you have the general group, you have the block group, and all of that. For example, if I select the field group, every result vector that I can select from here will have to do with the field, like field oil production rate, field gas injection rate, field pressure, and so on. And the same goes for group, well, aquifer region, and all that. We're going to learn more about how all of these results are named, but you can also take your time to come to the summary section, and whichever one you try to select from here, you'll see the name, the full name written down here. So you can try this, you can use the help of the manual or until the time we're going to talk about this fully. So I'll close this now. I'll close this as well, and then I'll go back to the result viewer window. So from the result viewer window, I'm going to click on File, Open Summary, Load All Vectors, and now I can select the summary vector file that has been generated from the simulation run. You recognize this file by this extension SMSPEC. So I'll click on the open button. This loads all the results that we have selected from the summary section. So the first node we have in this tree of data is the office project name, class_1, and E100 has been included to show that the simulation was run by Blackoil simulator. Then below that we have different groups of results, A for aquifer, F for field. So expanding the F folder of results, I can view any result I'm interested in here. Let's say for instance I want to view this one that says FOPR, that is field oil production rate. I'll simply double click on it and it's going to show me these results in the form of a chart. You can also view the results in the form of a table by clicking on this button here, and it's going to show you all of the data points that have been used to create this chart. If you don't like the way this chart is looking, you can copy this table from here, take it into Excel, and from there you can plot it and create the table the way you want it to look. So for now I am going to close this. Let's focus on this chart. The chart shows field oil production rate in barrel per day against time in days. I can change the unit of the time from days to something else by going to the view menu, and I select X axis, change it from day to date. If I click on the OK button, you can see I personally like to view my results like this. To me it looks better, but you can use whatever works for you. You can also display other information on this same chart. For instance, if I want to view cumulative oil production, which is named here as field oil production total, FOPT, I can right click on it and add to current graph, and it's going to be plotted on it. So you see we now have two different axes. One axis here for FOPR, the second axis here for FOPT. and then the blue curve represents FOPT, just as you can see from this legend here. Okay, this is basically how to view results, but what prompts the type of results you want to view is a different ballgame entirely. We're going to get to that. So let me go on to close the result viewer. Then we can begin talking about the data file. In the previous lesson, that is lesson 1, we talked briefly about the data file. We learned that it's an input file for the simulator, and it contains all the information which describes a reservoir that you're trying to simulate. So it means that this data file is an important piece of information. And I personally think that understanding the structure of this data file means that you understand the entire process of reservoir simulation and how the simulator works. Although sometimes you can have a very simple data file, and some other time, and in most cases, especially when you are trying to create a detailed, a robust reservoir model, you're going to have a complex data file which contains so much keywords. In fact, Eclipse itself has over 2,000 different keywords, if I'm not mistaken. So the problem is that how do we get to learn all of these keywords in one lesson or in this course? Practically, it is impossible to learn because it's like you are learning a new programming language. So it's going to require quite some time and effort. If you understand Eclipse data file, you can also use it for other type of simulators as well. For instance, I have run simulation on a data file which is meant for Eclipse on T-Navigator before, and it worked perfectly fine. In fact, the T-Navigator itself is a very powerful and popular simulator in the industry. It's very fast. So what it means is that if you learn about this data file and you understand it for Eclipse, you can also use it for T-Navigator as well. And that's a good one. Okay, so to make things easy for us, I have devised a very simple approach. What we are going to do is that we're going to work gradually. We're going to take it in bits. In this video, we're going to talk about the Runspec section and the Grid section. So when we look at these two sections and understand basic information in the data file that describes the information in these two sections, then in the next video, we come up with something else. And as we're doing this, we're going to be creating a simulation model. So I have this simple data here where I want us to begin from. All right. First of all, you should note that there are about 8 sections in the data file. And each of the sections contains a set of information which describes a part of the reservoir that you are trying to simulate. So we have the Runspec section, the Grid section, the prop section, which contains the PVT and core data, the region section, which is used to define compartments in the reservoir, the solution section, where you get to initialize your model, the summary section, where you get to select the type of result you want to view, and the schedule section, which contains information about your wells, your well specification, the production history data, and all of that. So we're going to deal with these two in this video, the Runspec and the Grid section. Now, the first thing you're going to notice at the top of this data file is that you have 2 dashes. And apart from that, you also have some other symbols like slash, and if you go down, you're going to see some other symbols like asterisks and so on. Then you'll notice again that some texts are written in bold letters, capital letters, and then you have other ones that are just written anyhow. All these things have different meanings in the data file. So I am going to start with these 2 dashes. Wherever you see a line of information in the data file, begins with 2 dashes, it means it's a comment. The comment is usually not part of the reservoir data, and the simulator also knows this. So once it comes to where a line of information in the data file begins with 2 dashes, it keeps it. It does not include it in the reservoir description. So technically, the first keyword we have in this data file is Runspec. And in the Runspec section, you get to enter general information about your reservoir. Case description, let's put it that way, because that's what we have in the Eclipse office. Case description. So this is where you get to enter the title of your simulation with the keyword title. And below that, we have the title, example simulation data file. Then the next keyword you have is dimensions. This one is used to specify the dimension of your model, of your grid. And we have a comment above it which says specify dimension of model, talking about number of cells on the x-axis, on the y-axis, and on the z-axis. So we have 10, 10, 3, right? Then here you enter the phases of fluid that you have in your reservoir model. So here we have just oil and water, and again above it you have a comment. Then what is the unit you are going to provide your data in? Field unit. Then you also get to specify well dimension. Now the Runspec section contains general information like I said earlier. So whatever you are trying to enter in the main body of your simulation data file, where dimensions are necessary to be entered, you first find them in the Runspec section. So there's going to be aquifer dimension, well dimension, grid or geometry dimension, and so on, anything. And then down here you have the simulation start date. When does your simulation begin? Most of the times this can be extracted from production history, where you have a reservoir that has been producing for some time. So the keyword for the simulation start date is simply start, and below that you enter your date. Now you also notice that slashes, whenever you enter in numerical information, you are supposed to terminate it by slash, and that tells Eclipse that this is the end of this information. All right. So the Runspec is very simple, very easy section, one of the easiest. So we'll now go on to the grid section. The keyword for the grid section is simply grid, G-R-I-D. And in the grid section, you get to define the geometry, the size of your grid, and this is going to be done by defining the size of each grid cell block. Now you have different types of grid, and that is where the complications begin to come in. For instance, the information we have in this grid section has been defined for this type of a reservoir model, which is called a block center type of reservoir model. Now the block center type of reservoir model, can I say, is hypothetical? Can I just call it a tank model? But most of the time it's an assumption. So you get to have something that is more irregular than this, a corner point type of grid. All right. But for a simple type of reservoir that we have here, in the grid section, you're going to define some kind of keywords, and they include dx, dy, dz, and tops. So dx, dy, dz simply measures the sizes of each of the grid cell blocks that we have. So what it means is that the length and the breadth of each cell block in this reservoir grid is 1000 feet each for dx and dy. And then we have 300 cells. How do we know this? If you go back to the Runspec section, from here, you see what it says, NX is 10, NY is 10, and NZ is 3. If you multiply all of this, you're going to have 300 cells. That is the total number of cells in the grid cell block. So after defining this, if you come to the grid section, you must ensure that whatever information you enter here as the number of grid cell block must agree with what you have defined in the dimension in the Runspec section. So from here we can see all of the 300 cells in this grid block has a dx or a length of 1000 feet, a dy or a breadth of 1000 feet, and they all have a thickness of 50 feet. That is what it means. Then this other keyword we have here is called tops. The tops simply represent the distance of the top of the reservoir, that is the first reservoir layer, from the surface. All right. So what has been entered here is that if you measure from the surface of the earth, that is on land, and then you take the measurement all the way into the subsurface where you have the first layer of the reservoir, is going to be 5,000 feet. Now remember, the first layer contains 100 cells. So the first 100 cells in the grid cell block is 5,000 feet away from the surface. The second layer, which also contains 100 cell blocks, is 5,050 feet away from the surface. And the third one is 5,100 away from the surface. And this is logical mathematically because each cell is 50 feet thick. Now, after defining the geometry, the next thing you want to do is to bring in the petrophysical information. So you have your permeability. All of the 300 cells have permex of 100 millidarcy. All the 300 cells have perm Y of 100 millidarcy, and they all have 20 millidarcy of vertical permeability, that is perm Z. I should also add quickly here that permeability is a vector measurement in the reservoir, so it's directional. So you're going to have permeability measured in the X direction, Y direction, and Z direction, and that is what we have captured here. Then next, you want to enter the porosity. The keyword for porosity is poro. And what we have here is that the first 100 cells, which is layer 1, have a porosity of 30%, layer 2 porosity of 23%, layer 3 porosity of 18%. So after entering all of this information, we can say that you are through with the grid section. But remember that what we have here is simple reservoir block, which is represented by this figure. Now let's go on to look at a more detailed, a different type of reservoir model that you can have. So this is the model that we are going to be working with in this training. And from what you can see, this is a detailed geologic model which has been created in Petrel by geologists. It's called a static model. All right. By looking at it, you will notice that we have more than 300 cells. It contains more than 70,000 cells, and it's heterogeneous. So what that means is that we cannot define information for 70,000 grid cell blocks the way you define for a box center type of reservoir with 300 cells with homogeneous properties. All right. So we're going to have to use a different approach, and the approach is that you simply come to the Petrel software and export all the necessary information from here and import it into your Eclipse project. Now I'll find time to talk more about this later on, but the objective of this video is to talk about the data file. So I have gone ahead to export all of the grid cell properties that we are going to need in the Eclipse simulation. So I am now going to leave here to show you how to import it into Eclipse.